Good morning, ladies and gentlemen. This is Ben Keyser with Applied Flow Technology. Hope that everyone is doing well and having a lovely Wednesday on this fine week. Before we get started, just want to do a quick live sound check with all of you listening in. If you're able to hear me, then go ahead and give me a virtual high five by clicking on the raise hand button. And that way I'll know that I can hear you. I'm starting to see some high fives going up. That's great. Perfect. Thank you for joining me this morning. I'm excited to talk about our AFT Impulse Pulsation Frequency Module analysis tool with you all. And I want to let everyone know that this webinar is being recorded. If you are listening in live, then my PDF of my presentation is attached for you. That way you can have it for reference for later. If you are listening into the recorded version, then please feel free to email me directly at benkeyser@aft.com, and I'll be happy to send you a copy of my presentation. That's benkeiser@aft.com. All right, I'm going to go ahead and get started. And one thing I want to point out is on our website, aft.com, there are tons and tons of useful resources that you can find on our website. And many resources will help you learn how to use the software more efficiently and effectively. If you go to aft.com, under the Learning Center, we have training seminars, case studies, tech papers. It seems you all know where the webinars are, so that's good. We have our upcoming webinars all scheduled out through the rest of the year here. And then our webinar library is where you can find the recorded versions of our webinars. Another area is our tips and tricks articles. We're constantly publishing new articles that will give you additional insight in our software on different topics. A lot of these come from common tech support issues. So be sure to keep an eye on this page. We're constantly adding new blogs to it. We've got probably a couple hundred blog articles that are really insightful, and we publish about 2 or 3 of them a month. So that's got a lot of good information available for you. Another area that I want to point out is our technical papers. We've got lots of them talking about AFT Impulse, surge analysis, automated sizing, which was previously with AFT Mercury, now the automated network sizing module for AFT Fathom and AFT Arrow. But the technical paper that I want to highlight today is several articles down. It's this one right here. It's called Pulsation Analysis in Positive Displacement Pump Systems using Waterhammer, Modal, and Animation Software. So if you open up that article, this is the article that Trey Walters and Jim Blanding wrote for the 45th Turbo Machinery Symposium back in 2016. And you can read the paper right here and get a PDF of it. This contains the full technical background and all of the details on what I'm going to be talking about in today's webinar. So if you want all of the guts of the information to really give you a deep understanding more on pulsation and things of that nature, then definitely be sure to read this article. That will give you a really solid understanding. So today I'm talking more on a high level of what pulsation is and then how you would model it with AFT Impulse. So this is the technical paper that will give you the full background of all of the information that you would want to know. Okay, so I'm going to go ahead and get started. The first couple of slides here is just boilerplate. This talks about our various AFT software products that we have available. I'm not going to go through these. I think that the majority of you are familiar with all of them. Again, if you want more information, simply go to aft.com and then under products, go to software overview. This will give you a bird's eye overview of each of our tools, and then for each individual product, you can find additional information. And then if you scroll down to that product page, this is where you can find details about the add-on modules that are available for that specific product. So the one that I'm talking about today is if you went to AFT Impulse and you scroll down to the bottom page, today I'm talking about this add-on module, Pulsation Frequency Analysis, PFA for short. All right, back to my presentation here. Okay, before jumping into the pulsation stuff, I did include several useful video tutorials for AFT Impulse. All of these videos right here that you see are based upon AFT Impulse version 6, but the layout, it's virtually the same as AFT Impulse 7. And these videos are critical if you're going to be doing water hammer analysis with Impulse. The quick start video, pipe sectioning, these 4 videos here talk about how to do the different types of transients in your system. These graphing videos are actually our new feature videos for Impulse 6. Those will give you a really good idea of how to use the graphing capabilities effectively, because in AFT Impulse version 6, we came out with brand new graphing abilities that will revolutionize doing water hammer analysis. So certainly be sure to check out those videos there. In addition to the video tutorials, I also provided some direct links to a few of our previously recorded AFT Impulse webinars. And so that will give you some more good content on doing water hammer analysis as well. All right, so let's talk about frequencies and resonance and vibration and oscillation. What is all of this stuff? So every physical system, whether it's a piping system or a bridge or the human body or wine glasses, when people would make wine glasses hum, every system has a natural frequency that will cause it to vibrate and oscillate. And you can excite those natural frequencies with outside forces, and it could go into a state that's called resonance. And what resonance is, when the natural frequencies are excited, those vibrations will grow stronger and stronger over time, and that can amplify the vibration or oscillations that you'll see inside that system. Again, a good example of wine glasses, or the opera singer that's singing and she shatters the all the windows. Those windows would be oscillating at their resonant natural frequencies, and then eventually they shatter. So that's what we're talking about today. If you have a strong enough energy source, or if your system is weak enough, it can tear itself apart and become, it can be destroyed. If it's not destroyed, then constantly exciting those natural frequencies will certainly cause issue of the system, and it'll weaken it over time to where it will not perform in a proper fashion. And so a lot of ways that engineers will address vibration issues is by changing the stiffness of the system or the mass. That can help reduce vibrations in most cases. So I wanted to include some examples of vibration here, and I've got a couple of videos that are useful. One note that I want to point out is if you have vibrations that are not at the resonant frequencies, those will typically be small and they may not be problematic, but they certainly can be if your vibrations are at or close to the natural frequencies, and that's where your system will start resonating. And that's any type of system. So there's a really useful video that I want to highlight, which really does a great job of explaining vibration and resonance and what all of this means. So I'm going to turn on my external speaker, and I'm going to access this video here.
Powering on. Welcome to all.
Give me just one moment here while I switch over to a speaker.
I just want to make sure everybody can still hear me. And let me, I still got, let's see here. Okay. I want to do a quick test, everyone. I was switching over to using my speaker device to play this video. So if you all can still hear me, give me another virtual high five with the raise hand button. Is anybody able to hear me? Testing, testing, testing.
Well paired. Enjoy.
Testing, testing, testing. Is everyone able to hear me? Okay, good. I've got some virtual high fives. Perfect. All right. So I'm going to go ahead and play this video. This is in terms of buildings, but it gives you really good representation of what's going on.
The different building models, my favorite. You can block it with a wheel Junction, back and forth, simulate earthquake hydraulics. And these are dial sticks of different lengths with blocks of wood on top. So you've got tall building representation, not the short building. And I like, if there's a group of people, a group of kids, ask them, which building do you think would move around the most in the earthquake, which will move the most in the earthquake? And very often they will pick the tall building. Because it's obviously it's moving around, it seems a lot like by itself right now. But so then I generate this thing. I vibrating the ground. Oh my goodness. The short building has moved the most. Okay, well, now you know what the answer is. You get one more guess. So now a lot of people change their guess and say, well, maybe the short one moves the most. So now I make another and say, well, this type of equipment. Oh, lo and behold, it's the tall one now that's vibrating the most. So at this point, I think it's good to have a question and issues for kids to think about for a second. Okay, now what's going on? What's the centric to this? What is he doing differently between the short building moving the most and the tall building moving the most? And so then I explained that, well, it actually has to do with the resonant frequency of each of these buildings, which is quite different. The resonant frequency is the frequency the building wants to move back and forth. You just give it a bump. You can see the short building moves back and forth very quickly when you just pull it and let it go. The tall building is very slowly. And you move with intermediate frequencies. So if the ground motion is the same as the resonant period, resonant frequency of one of these buildings, the amplitude of building motion will build larger and larger. So if I move the ground very rapidly back and forth, I'm getting a resonant frequency near this one. You see the amplitude there, it's very large. And if I go very slowly, all buildings moves large. And you can also go at intermediate frequencies. This one.
All right. That's an excellent video for getting a really good conceptual understanding of vibration and pulsation and resonance. And I know that the sound didn't come through very well, but in the presentation, there's a direct link to that video. That way you can watch it again on your own. So as you saw there, the buildings of different heights would shake, or i.e. vibrate at different frequencies depending on how fast he was moving the little truck back and forth. And so depending on how fast he was moving the truck back and forth, the speed, essentially, then that would cause different buildings to vibrate in different ways. And once they started vibrating, they were at their resonant frequency. And that's what will eventually tear the buildings apart. I have another video that I want to show here is actually examples of vibration in piping and small bore vibration. So here's another video that will illustrate what's going on in our realm here. So let me go ahead and play that. Some of the still images in this video show damage of different parts and pieces of the piping system, but it's hard to see what those issues are, but you can definitely see what's going on in problems like this, with pipes shaking all over the place. Awesome. I think that you get the idea. For the sake of time, I'm going to keep moving forward now, and that gives you a good idea of some horror stories
Powering off.
in piping systems that will destroy the system. And there's a few other videos that I have in here that you can watch again later at your leisure. There's another one with a piping network, which visually shows what's going on, but there's no sound in that video. And then, of course, the good old-fashioned Tacoma Narrows Bridge, of that bridge tearing itself apart when the wind was blowing way back in 1940. So you can watch those at your leisure. Since I switched back over to my microphone, just another quick test. Give me a virtual high five if y'all can still hear me okay. Perfect. I'm getting some high fives. High five back to you all. Thank you. I'm going to keep moving forward. So let's talk about vibration resonance a little bit more. The piping systems, especially the ones that you saw in that video, they can vibrate in different ways. One is with the pipe material itself. This is called mechanical vibration. So if you have vibration that is operating near the natural frequency, then that's what would be called mechanical resonance. That is not typically that's not really something that AFT Impulse is going to predict. That's something that your pipe stress analysis software packages will be able to model. So they'll be able to tell you if you have mechanical resonance in your system. Then you can have fluid inside the pipe that is vibrating and resonating. And so this is actually called different things. There's acoustic vibration, fluid vibration, hydraulic vibration, etc. So when the vibration is caused from the fluid inside of the pipe, we will call that here at AFT acoustic vibration or acoustical resonance. So if you're doing a pipe stress analysis with a pipe stress software, you would see all sorts of different vibrations throughout the network. And they would either be mechanical vibrations or acoustical vibrations. What AFT Impulse will be able to do is it'll be able to tell you which frequencies are acoustical. And that way you can avoid operating the pumps at those particular speeds. So in a piping system, one of the common sources of resonance and vibration is with positive displacement pumps. They represent up to 30% of all pumps. Maybe that figure is a little bit different, so I'm not sure, but they certainly make up a really good handful of the pumps that you'd be working with. If I'm not correct on that statistic, don't beat me up on that. There's a lot of PD pumps out there. That's all I'm trying to say. So when you're dealing with pulsation from positive displacement pumps, the oscillating flow through the pump can be at the natural acoustical frequencies, and that will cause acoustical resonance, which can tear apart your system. These are some additional videos that talk about how positive displacement pumps work, and these are really good videos that illustrate the intermittent flow through PD pumps. And if you watch those, you'll be able to see how that flow oscillates, and that'll probably give you a better picture of what that acoustical resonance would look like and the impact it would have on your piping system. I'm not going to play any of those videos today, but you have the links to them here in the presentation. So when you have that acoustical resonance, it can cause your piping to vibrate just like in the videos, and destroy your piping or your joints or pipe supports, and it can certainly disrupt your production process quality. So certainly something that you want to make sure that you avoid. So AFT Impulse has always had the ability to model positive displacement pumps very easily, even in several previous versions. It would be something even as simple as modeling how the flow rate through a positive displacement pump changes over time. So Impulse has always had the ability to do that. What the Impulse PFA module will do is it allows you to predict what those resonant frequencies are. So that's not something that was available before. That's what's available with the PFA module, is calculating those resonant frequencies. The technical paper that I showed you talks a lot more about the details on how that is done behind the scenes. In addition to predicting the resonant frequencies of those PD pumps that you want to avoid, you can also have Impulse automatically create child scenarios. That way you can actually see what the transient pressure response would be if you are operating your system at those frequencies. And then you can compare those pressure pulsations to various standards, mainly the API standard 674. And actually in AFT Impulse with the PFA module, it'll do that comparison for you. So we have the API standard 674 built in, such that if your pressure pulsations are outside the bounds of allowable pressure magnitudes from vibration, it'll give you very clear warnings that your pulsations are way too high. And you're actually going to see that in the example that I'm going to be demonstrating for you today. So here's the example of the system that I'm going to illustrate. The two positive displacement pumps that I have in that system are simply being modeled with assigned flow junctions with fixed flow rates. And this is essentially modeling the discharge part of the system downstream of the positive displacement pumps. There's an important note that I'm going to make on this here in the next couple of slides. But one of the things that we found in this particular system here is that there's a severe pulsation problem that's happening in this particular pipe, which is connected to an isolation valve that is closed. That isolation valve is simply being modeled with a dead-end junction where there's no flow through that path, but this is a reflecting point. And so you will see pressure and velocity waves reflect off of that closed valve, and you can see how the pressure will pulse in that particular pipe. So that's the main problematic area that we're concerned about. But the thing is, when you have pulsation issues going on, you can have different frequencies in different pipes. So in some pipes, you may have a resonant frequency where you don't see the same frequency in other pipes. So when you're doing this type of analysis, it's really important to be sure that you look at the whole thing to really see what's going on. All right. So our goal of this example is to determine what those natural resonant frequencies are, and then to evaluate the pump speeds that will excite those frequencies That way we can actually see what the pressure response will look like if that happens. So the steps that you will do to accomplish this is, first, you're going to have to ring the system. You smack it with a mathematical hammer, and that's what will excite your acoustical frequencies. If you remember the video of the guy with the buildings, that mathematical hammer is when he would grab one of those buildings and pull it back and let it go. That's the mathematical bump that we are giving the system to figure out what the natural frequencies are. After we've figured out the natural frequencies, we will need to determine what the pump speeds are that will cause those frequencies to happen. And then finally, we will create our scenarios, and we're going to run the model at those bad pump speeds, and we're going to see what the pressure response looks like when those resonant frequencies have been excited. So this is what we're going to do today. The very first thing that you would do when you run Impulse is to turn on the AFT Impulse PFA module. So when you first run Impulse, this is the standard checklist that you're going to see. This is the yellow brick road that you want to follow to building and defining the input of your model so you can get results and do your analysis. So if you're brand new to Impulse, the very first thing that you should do is click on this red status light that's down at the bottom right corner of the window, and that pulls up the checklist of all of the items that need to be completed before you can run your analysis. So your solution control, your fluid properties, building and defining the input for your pipes and junctions, sectioning pipes, and defining your transient control. I'm not going to go into details on what any of those things are today. I'm going to assume that you all have a bit of an idea of how to use Impulse. If this is your first time seeing Impulse today in this webinar, then be sure to watch those other video tutorials and webinars that I highlighted earlier in the slides. Now, in order to enable the PFA module, what you'll do is click on the button that is just to the left of the status light, and then simply check the box of the PFA module. That is something that you would have to have a license for, so you need to get a license for Impulse and the PFA module. And then once you turn on the PFA module, it actually slightly changes the checklist. Now, if you pay close attention to this here, the first three items of the checklist are the same as they were before. Solution control, fluid properties, and defining your system. All of that is the same process that you'd be doing before, so nothing is different about that. However, the difference is that you have this new checklist item to specify your pulsation setup, and that's what's going to cause the pulse of your system to determine the natural frequencies. And then you actually section your pipes at the very end. And so you're going to see what this looks like here in just the next couple of minutes. So it slightly changes your checklist, but again, follow that yellow brick road, and that'll help you quickly be able to do your analysis for your pulsation study. Now, what I'm going to do is I'm going to start with a pre-built and partially defined model. So I already have the model of my system fully built. I have all of my piping defined, and one of the things I want to point out is the piping definitions are more simplistic. This is simply specifying the hydraulic diameters directly. It's not using any common pipe material like steel or nominal sizes or things like that. It's very simplified. So we're doing the hydraulic diameters directly, and then on top of that, what we're also specifying directly is the wave speed. So that will dramatically simplify the model definition process for the piping. I'll show you an example of that when I get the model pulled up here in a minute. All right. Now, I want to make a couple of quick notes on modeling positive displacement pumps in AFT Impulse. You can model them in a few different ways. One way is to use the assigned flow junction, which is actually what I'm doing in the pulsation model here. And what you can do is on the transient tab is specify a time transient of this cyclic flow behavior. So if you specify this data for the flow oscillation through your PD pump, you can click on this repeat transient button and you'll see this graph here. This is how your flow rate changes through your pump over time. So this is one way to specify your PD pump behavior in probably the most simplistic fashion. Another way is to use the actual pump junction, like this model here before. So if you use the pump junction, you can choose positive displacement as your pump, and there's 3 ways to do it. The steady way is simply a fixed flow rate. This is typically what you would do in AFT Fathom. If you're modeling a PD pump in Fathom, it's really just going to be a fixed flow rate because that's the average flow rate that you're going to see over time. Now, the second option that's available here is to use a simple periodic flow change, and that's where you can specify some basic input, such as your average flow rate, the number of heads, and the operating speed, and that'll give you this flow characteristic here, which is calculated for you. If you want to be a little bit more fancy, in AFT Impulse version 7, there's this new option where you can use the detailed fashion here. And the detailed fashion allows you to specify not only your operating speed, but also your bore, your strength, and your rod length. That will calculate what your average flow rate is based upon the number of heads, and then that will give you this flow characteristic right here. So that allows you to be a little bit more complex for your PD pumps. So just another method. Those are 2 different ways that you can model PD pumps in AFT Impulse. Now, this is the important note that I want to make on the PD pumps in AFT Impulse when you are dealing with the PFA module. With PD pumps, you typically will have some sort of check valve on the pump where the check valves will open and close based upon your suction and discharge strokes, which allows flow into the pump, and then when you're discharging, it'll push flow out. So the thing is, when you have your PD pump operating on its various suction and discharge strokes, the flow through the pump is going to be intermittent. It's not going to be continuous through the pump at all times. You'll see that very clearly if you watch the videos on how the PD pumps work. Very good illustrations of the oscillating flow behavior. So because the flow is not continuous through the pump, your suction and discharge sides are actually isolated from each other. So one of the key things that you have to remember and keep in mind when you're dealing with the PFA module is that you have to evaluate the suction and discharge piping around your positive displacement pumps separately. That's why, if I go back a few slides, that's why I have broken my system right here with these fixed flow pumps, and I'm modeling the discharge piping of the system because it is cut off and isolated from the suction based upon the opening and closing behavior of those check valves and the intermittent flow. So that's a key concept to remember when you're dealing with the PFA module. All right. In order to do your pulsation analysis, you have to smack your system with that mathematical hammer. So just like how I've done, I'm using a assigned flow junction for both of my PD pumps, and you will specify a flow rate, which is your initial flow rate in steady state, and then on the transient tab, you're going to have your flow behavior for your mathematical hammer. So this data here is the hammer that is going to ring your system to determine what the natural frequencies are. Now, here's the thing. You don't have to specify that on your own. It's not something that you have to come up with for your analysis. We will actually do that for you based upon your positive displacement pump definitions. So when you are setting up your model and you're defining your input, initially, the only thing that you need to specify is this initial flow rate. You don't have to specify that transient yet, because what's going to happen is in my next slide right here, you're going to specify your pulsation setup in the 4th step, and you will specify your setup tab and then your PD pump settings. All of this information is what is going to create your mathematical hammer that's going to ring your system. So when you specify all that information, that's what will create this profile for you. All right. And then finally, after you specify your pulsation setup, you're going to section your pipes, and that's what will break the pipes up into bits. And one of the key things in this system is that pipe 8 is not going to be considered in a pipe section. It's a very short pipe, which is simply modeling a flow meter. So this is where we have the ability to ignore that pipe. Where is that pipe in the system? It is right here. So this is our flow meter. We've got a contraction and then expansion and a really short pipe, and that's how we're modeling a flow meter. And this is just part of the example that is in that technical paper on our website. So now that I have outlined what's going on here, I'm going to move my presentation out of the way, and I'm going to cut to my model here. So as you can see, I've got the model of my piping system almost, well, it is fully defined. I've got my solution control, fluid properties, and my input all defined. The fluid properties that I'm specifying here are very simplistic. It's just a user-specified density, viscosity, and bulk modulus. So that's all it is. If you look at the pipes here, this is where you can see that I'm modeling what the inner diameter is directly. And if you click on the user specified option and you specify your wave speed directly, it's a lot more simplified. If you use the calculated option, then what would happen is you would check that box, and then there are additional pieces of information that you had to specify in that case. So those are two different ways to do it. I'm using just a simplistic way here. We've got a spray discharge nozzle at the outlet of the piping system. And so we've got our discharge coefficient and a discharge flow area. And then finally, we have our isolated valve, which is just modeled as a dead-end junction for simplicity. And then this is our section of pipe that has the significant pulsation issues. And so it's got a really small inner diameter, and it's about 21 feet long. Now, the positive displacement pump that I'm going to ring the system with is this one right here. So for this particular pump here, we've specified the flow rate 35.5 gallons per minute. Now, I'm going to go on to the next step to specify my pulsation setup. So once I click on that, it pulls up the window where I do all this information. This is a slight modification to typical impulse settings. So this is not where you're going to specify your time frame. You're specifying different things. So I'm going to use variable pipe resistance here. The pulse is going to be applied at J2, and my start time is 0. And then a lot of this is already specified for you naturally. So the magnitude of that mathematical hammer by default is going to be about twice what your steady state flow is. So that's calculated directly. And then you would identify your pulsation source. So this is where you can do your positive displacement pump. Maybe your pulsation is caused by something else. That's where you can do other. So here in our PD pump, we've got 3 heads. We have 250 RPM for the pump speed, and then there's a buffer. The technical paper talks about what that is. And then we have various low-pass filtering that needs to be done, and then a cutoff frequency. All that is defined for you. I'm not going to go into detail on those settings. That's documented in our help file as well as the technical paper. Then finally, to finish things off, is my PD pump settings. So you just go in here and you fill out this information. So I'm just going to go right down the list, and I'm simply copying and pasting in the values from my PowerPoint slides. That's why I moved it out of the way. And now I would have to go in and specify the units. So all these are going to be in inches, and then the pressure is going to be in PSIG. So my suction pressure on the PD pump is 50. My discharge pressure on the PD pump is 6,000. After that's all specified, then just click OK, and you get your green check mark, and you're done with that item. Now we can move on to section our pipes. So I'm going to click on section pipes, and this is done a little bit slightly different than typical sectioning with AFT Impulse. So if you remember, pipe P8 right here is our flow meter. I'm not going to include this pipe in the sectioning because that's going to increase our runtime since it's a really short pipe. So I'm going to scroll down this list, and I'm going to uncheck the box for P8. Now I can re-update my results, and I'm going to use one section in the controlling pipe, and then all of this information here is defined for me. The tech paper talks about this in more detail, and what I want to show you is the pulsation graph. So if you click on this button here, it'll show you the pulsation graphs that are important for causing your mathematical hammer. So this pulse, this is your hammer that's going to ring the system to excite the natural frequencies. Next, you can do your FFT, your low pass filter, and your FFT of the low pass filter. That's stuff that I'm not going to get into today. So again, read the technical paper, and then I'll go into more details about those settings, but you can get those graphs right there. And then we'll click OK. And what the sectioning does in the specifying of the pulsation setup is that's what will create the transient for our PD pump. So now you see the letter T next to that assigned flow junction. That means that I have a transient defined for that location in the system. So if I open up that assigned flow, I now have all of that transient definition specified. And then right over here at time 0, that's my mathematical hammer that's going to ring the system. And this is how I'm going to figure out my natural frequencies. That's all that you have to do. It's really quite quick and easy for being able to get that all set up. So now you've got all green check marks and a green status light. We're ready to run the model. So to run the model, you just click on the green arrow that points to the right. That's the same thing that it's done before. This is our water hammer assistant. This is really important to read because it gives you some insightful information about things that may or may not apply. This is giving me a message about that assigned flow junction. I am ignoring it because I am modeling the assigned flow properly for what I'm trying to do in this pulsation analysis. So now we run the model, and this is going to do the impulse run where it calculates what the excitation frequencies are. It doesn't take too long for it to run, thankfully, here. And just to give you a precursor of what we're going to be looking at here when that's done, is we're going to be able to generate some new types of graphs that do not exist in standard AFT Impulse. So we're going to create some graphs of the frequencies. Now, one thing to keep in mind is just like standard normal AFT Impulse, Impulse has to section all of the pipes and break them up into bits where there are multiple computation stations along each pipe. That has to be done so that the method of characteristics can calculate the new mass flow rate and the new pressure at each time step during the transient water hammer analysis. Same thing is going on here with using the PFA module. That sectioning still has to take place. So when you have all of those different computation stations, you're going to have potentially different excitation frequencies that can cause resonance. So what we're going to look at when we do the graphs here in a minute for looking at our excitation frequencies, the only thing I'm looking at right now is the inlet and outlet of pipe P1, P2, P3, P5, and P6. I'm only looking at the excitation frequencies for those 5 pipes at the inlet and the outlet. Keep in mind that there are several more interior pipe stations in each of those pipes. And in order to get a full picture, you will have to graph the excitation frequencies for all of the different pipes in your model, because you may have issues in other areas, and that's where you have to look at everything together. So right now, I'm only looking at a very small portion of the system in terms of the excitation frequencies there. All right, the model is done running. Let's take a look and see what's going on here. If we go to the output table, this is the same thing that it was before, but something that's nice is this pulsation summary. This will give you a summary of everything that you specified in your pulsation setup window here. That way you can print out this information and go back to it. But the graphing is what we're going to need to do. So I'm going to go to the graph results window. At this point, I'm going to collapse my quick access panel, or not my quick access panel, my checklist. That way I can move it out of the way. And what I'm going to do is I'm going to go to the frequency tab. This is what's available when you turn on the PFA module. So the first thing is on your frequency tab. This is where you list out which individual pipe stations that you want to plot your excitation frequencies for. After you generate that, you would look at the different frequencies, and eventually this field will come into play here in a little bit. So what I'm going to do is I'm going to add the inlet and outlet stations for those 5 pipes. So here's P1, inlet and outlet, and then I have P2, inlet, outlet, and then P3, inlet, outlet, P5, inlet, outlet, and then P6. Again, P6, this is the dead leg, and I'm going to generate my excitation frequencies in the plot here. So this takes just a few seconds because it's having to plot thousands of data points of data. So don't be worried when you see that it's not responding. It is actually doing things. You just have to wait for a sec. Right now, with doing the GoToWebinar, it might have just a bit slightly longer of a delay. So we'll just give it another second or two and let it do its thing. And there it is. So let's break this down. I'm going to uncheck the data for all these pipes, and we look at things one by one. So let's see what's going on in pipe P1. These are the excitation frequencies that are happening in pipe 1 at the inlet and the outlet. So the peaks that look like they might be kind of severe would be right here and maybe right here. So that's what's going on at the inlet and outlet of pipe P1. And we've got P2, which has some similar frequencies, but as you can see, there's a much higher amplitude on this peak right there. And then we can just keep on adding on additional data sets. So pipe 3, that's the blue and the orange, and then we have P5, and then P6. As you can see, the outlet of P6, this has a really high frequency. So what you want to do once these high peaks are identified is you're essentially going to add these large peaks over here, and you're going to translate those into speeds for the positive displacement pump. That's going to tell you what pump speeds that you need to avoid operating at. And it's really easy to do this. So let's start with this particular peak right here. I want to send this peak over to be evaluated at a certain pump speed that's going to excite this particular frequency. So here's how you do that. You just take your mouse and then with your left mouse button, just click and drag. As you can see, I have that little tiny window where I can hover over a certain frequency range and let go. Once I let go, it's going to tell you the amplitude as well as the frequency of that particular spike. So at the outlet of P6, the frequency, which I have the highest peak, is at 32.6 hertz. Once I have identified that, I will right-click on this text bubble and click on Evaluate Excitation Frequency. Now, what that will do is it's going to go ahead or it's going to do a whole bunch of math behind the scenes, and it's going to take that frequency and based upon various harmonic multiples, it's going to calculate the pump speed that will excite that particular frequency. So that's all done for you. You don't have to do any of that math-magic yourself. Let's do another one. I'll highlight over this peak here at 28.9 hertz, right click, and I'm going to evaluate that excitation frequency. So the pump speed that excites that one is 192 RPM. Now let's take a look at this particular spike right here. Okay, that's a really high pressure, or that's a really high amplitude that kind of concerns me. Well, if I do the same thing where I click and drag, what this is going to do when I try to right click and evaluate the excitation frequency, it brings up this message and it tells me this frequency of 6.1 hertz has no excitation pump speeds that are between my minimum and maximum pump speed. So here's the thing is when you're going through and you're specifying your pulsation setup, either from the analysis menu or from the checklist here, and then you enter all of your different PD pump settings, it's going to be able to figure out a minimum pump speed that your pump is going to operate at and a maximum pump speed. And so this could be either revolutions or rotations per minute, or it could also represent strokes per minute. So that's your pump speed. And what this message is telling you is that, yes, this is a excitation frequency, but that's occurring at a pump speed that is outside the range that your pump would ever operate at. So you don't even have to worry about that excitation frequency. You can ignore it in this case. So that's why it does not add it to this list of excitation frequencies. But let's do this tiny little one right here. I missed it. Let me try that again. So this is a frequency at 7.1 hertz. If I evaluate that, that's going to occur at a pump speed of 142.1 RPM. So now what I have is 3 different pump speeds that I have identified based upon their excitation frequencies. What I want to do is create new scenarios where I translate all of this information into a transient profile for the pulsating flow through my PD pumps at those particular speeds, and I want to evaluate the pulsation response from that. So here's the final step. What I'm going to do is click on this button down here to create scenarios based upon my selected pump speeds. So I click on that, and it's going to create 3 pump speed scenarios with flow rates that will correspond to these speeds and frequencies. Do I want to continue? Yes, I do. So now it's creating my child scenarios for me, and that's all done. So now what you would do is you would load each of these individual scenarios, and you're going to look at the pulsation response for each of them. Because you've already smacked the system with the hammer, now you're going to see what the response looks like when it's like the truck moving back and forth in that video, causing the buildings to shake. How much of those buildings going to shake? So that's what we're looking at here. So I'm going to double click this scenario. And once I double click that scenario, if I open up this PD pump, this has now been changed. So now I have my new transient information. This is the actual flow that's pulsating through that positive displacement pump based upon all my PD pump settings and the appropriate pump speed based upon that excitation frequency. So this is the flow profile that we're going to evaluate, and we're going to see what happens in that particular situation. So I'm going to run this scenario, and it's going through and it's running the various parameters. This doesn't take too terribly long. The key thing is when you're looking at each of these scenarios, what we want to look at is what does the pressure response look like in this particular pipe. You can look at the pressure response everywhere in the system, and you can do the same types of animations that you would do before, but the key thing is that we know that we have a problem in this pipe right here, so that's the only pipe that I'm going to focus on during this webinar here. So we would look at that for each of these different scenarios. We would also compare the pressure fluctuations based upon that PD response, and we would compare them to the allowable pressure fluctuations based upon API 674. So this is almost done here, hopefully, with the transient solver. Hopefully you all are able to see that this whole process is actually fairly simple. And if all you're doing is pulsation, you don't necessarily need to know all the guts about how to use AFT Impulse. I would recommend that you should know how to use Impulse, but if you're trying to do a pulsation study, it's as simplified as you see that I'm doing it today. You might just need to get a little bit more exposure on the process of how do you build your model, how do you input information, how do you specify your fluid properties. You might need to become a little bit more familiar with what wave speed is, what pipe sectioning is, and what different transients are. But ultimately, once you've got that all under your belt, doing the pulsation analysis here is easy. And it's really just a few quick and simple steps. The major advantage is that when you have AFT Impulse with the PFA module, you can do your own pulsation analysis at any time for any system rather than having to hire someone to come out and do a vibration analysis for you at $30,000 a pop or whatever it is. Okay, so here are the results for this scenario where my pump is operating at 142 RPM. So it does check what the API 674 pulsation and pressure limits are, and it will tell you the applied standards for that. So it looks at if any of the pipe stations have peak-to-peak maximum pressures that are outside the allowable range for the API standard. It also checks the pump inlets to see if the minimum inlet pressure is above the vapor pressure as well. And so this is telling us that we do have some peak-to-peak pressures which are outside the limit at several different locations. So this is not good. This is why you want to know where those excitation frequencies are happening and what your pulsation response looks like so that you can determine if you're within code compliance or not. So here's what I'm going to look at. I'm going to go to the graph results window. Now I'm going to do a profile plot of only pipe P6, which is only 21 feet long. Now I'm going to take a look at both the pressure as well as doing an animation. Now I'm going to scale in on my axis here. So I'm going to right click on my axis and I'm going to make this go out to 22 feet. So I've modified my x-axis. I'm going to modify my y-axis. I'm only going to go from 4,300 to 4,400. And I'm going to do every 10 psi. So this is pipe 6, okay? The inlet of pipe 6 is here. The outlet of pipe 6 is here. This is right where that dead end is, which is the closed isolation valve. So now when I play the animation, you can see how the pressure oscillates between the maximum and minimum pressures that we see. So when the positive displacement pump is operating at the various frequency and pump speed, this is the response that we see in this particular pipe based upon that flow behavior. So this just gives you a full picture of what's going on. So that's that scenario. What we would then be able to do is we would transition to another scenario, and we would look at essentially the same thing, but you'd probably want to also look at all the other pipes in your system. In this last scenario, which is the highest speed and the highest frequency, where we saw the really high amplitude, is the pulsation. It's much, much higher. And for the sake of time, I'm not going to run that scenario right now. But what I will tell you is that the minimum and maximum pressures for this particular pipe, when you're operating at this pump speed, is much, much further apart. So that's where you have an even worse issue if you're operating at that pump speed. And that's the beauty of what the AFT Impulse module will do. It's as simple as going through this checklist of initially building and defining your piping system in the same way that you would do with AFT Impulse like normal. And then the two new steps is to simply go in and specify your pulsation setup. This is where you're going to identify what is going to ring your system to determine the natural frequencies and how it's going to do it with your various pulsation and positive displacement pump settings. You'll section your pipes slightly differently than you would normally do. And then once that's all done, you just go through, run the analysis, go back to your base scenario where you have determined what your natural frequencies are. That's my base scenario. And then based upon those natural frequencies, evaluate the pump speeds that can cause those frequencies to happen, and evaluate your pulsation response. It's as easy as that. Well, thank you all very much for your time. Well, before I end, the next thing that you would do after that is you could then start implementing measures on how to mitigate that. And an excellent way to do that is by using some pulsation dampeners. You can model that with gas accumulators, maybe a surge tank. There are excellent companies out there that build pulsation dampeners that can help you mitigate those surges and pulsations in your system, like Blaco. Giving a shout out to Amy of Blaco, and they will do a fantastic job at helping you figure out what type of pulsation dampener that you'll need once you have all these frequencies in place. Okay, thank you all very much for your time today. I appreciate you listening in. If you have any questions, please don't hesitate to give us a call or feel free to contact your local channel partner. They'll be glad to help you, and we'll get you up and running with AFT Impulse with the PFA module. Take care, everyone, and have a wonderful rest of your week.